Assalamu alaikum. Can you people hear me clearly? Okay, so welcome to the class of microwave engineering. Sorry for some delay in the starting of class because of some urgent work. Okay, so last time we discussed two types of impedance matching circuits, that is L networks and single stub matching. And we went through the whole design procedure using spec chart. Today we are going to talk about another stub matching circuit, but this circuit now involves the use of two stubs. And because of that reason, it's known as double stub impedance matching circuit. Now, before talking about the operating principle of double stub, we also need to understand why we need double stub impedance matching circuit. What is the problem with the single stub matching circuit? So let's talk about limitations of single stub. Okay, so one of the limitation of single stub circuit is that if you design a single stub matching circuit and after some time the load impedance changes, so as a result you have to change the position of the stub. So every time the value of the load impedance changes, you have to connect your stub to a new position, which means you have to remove the stub from its original position and then connect it to another new position. So every time this happens, you have to keep on changing the position, and whenever position of the stub changes, you also have to change its length as well. So in some application, this is not desirable. We don't want to keep on removing the stub and connecting it again and again. Okay, so the limitation is for changing for changing load impedance, we need to change the position as well as length of the stub. Now, changing length of the stub is not an issue. From practical point of view, length of the stub can be easily changed. Okay, so this is can say this is not a problem. The problem is changing the position of the stub. Okay, so that is basically what you can say not what we want. Okay, so we need some other type of stub matching circuit where whenever load impedance changes, So even of course in practical circuits, you will be dealing with those situations in which the load impedance is changing. So for that type of situation, we need some kind of impedance matching circuit where we don't need to change the position of the stub. Length of the stub, this is not an issue. We are comfortable with that. We are not comfortable with this thing. Okay. So this problem or this limitation of single stub matching circuit, it can be compensated by using this circuit, double stub. So that is what you can say the advantage of double stub impedance matching circuit, that even if the load impedance changes, you don't need to change the position of the stub. So using double stub, we can avoid changing the stub positions even if load changes. So that is the use of double stub impedance matching circuit. So let's look at the configuration of double stub. So again, it's just like in case of single stub, we can connect the stub in series configuration or in shunt configuration. So in a similar manner, we have two types of double stub from configuration point of view or from connection point of view. That is, we can connect both stubs in series or we can connect both stubs in parallel. So let's consider both of these cases. So this is our main transmission line. So we have this original problem that our transmission line with characteristic impedance Z0 and our load ZL not equal to Z0. As a result, we have an impedance mismatching problem, reflection coefficient not equal to 0. And we want to solve this problem with the help of double stub. So what are two possibilities? So let me draw the first possibility. In the first case, we will connect, let's say, stubs in shunt configuration. So one stub will be connected. Again, you can connect the stub at any position, but it makes our analysis quite simple if we connect the first stub right at the position where load is connected. So this is the position at which load is connected. So at these 2 points, we will connect one stub in shunt configuration. Okay, so this is stub number 1. And the parameter that we will find out is L1. So we will find out what should be L1. Of course, it will depend upon the value of ZL. And again, just like in case of single stub, this stub can be either kept as open circuit or we can also short circuit it. Both are possibilities, and the designer has to decide which one is convenient for him. So the first stub we have connected right at the position of the stub. Now the second stub will be connected at a fixed distance from this one. So let's the practical distance. So this can be at some distance, fixed distance, but you will find out that from practical point of view, this distance is either kept to be equal to lambda by 8, or it is kept as 3 lambda by 8. So as I'm telling, this is fixed. You either connect the second stub, so there we will connect second stub. So this second stub can be connected at a distance from first step, either lambda by 8 or 3 lambda by 8. So now we will connect another stub over here. And again, this can also be either open circuit or short circuit. And this is going to be the length of second stub. So as I was telling you, if this load changes, okay, if this load value increases or decreases, so what will happen? You will not change the position of the stub. Stubs will be connected permanently at these 2 points. All you need to do is change whenever ZL changes. So you have to find out the different value of L1 and L2, which will make your circuit matched. Okay, and the idea is similar. What is that idea? Why we have connected these two stubs? Because we want that any signal which is now coming from this side, when it reaches to this point, so let me, so this is the point impedance or input point of the stubs. So now this signal, when it arrives at this point, it will feel as if there is a match load connected on the right side. So as a result, now reflection coefficient will be 0. So for this signal, it appears as if now it is supplying power to a match load. Okay, so we will find out how this happens. What is the effect of these two stubs so that we get this condition? But this is one possibility where we have connected both of the stubs in shunt configuration. So this type of circuit is known as shunt double stub matching circuit. Okay, and it is also possible that we will connect the two stubs in series configuration as well. Okay, so let me draw that possibility as well. So now the same problem can be solved with the help of series. So now what we will do, we will make one cut in the cable. So now this is the load. So this load, now there is series stub, and we will connect our stub at this point. This is again open circuit or short circuit. This is our stub number 1, and this is the length of that stub, and again at some fixed distance. So at a fixed distance, either lambda by 8 or 3 lambda by 8, we will connect our second stub. So what is our goal? Why we have connected these two stubs? So now we want that if we look towards the load at this point, we want that this impedance should be equal to Z. So this main transmission line is Z naught. So when signal arrive at this point, it will see as if there is this value of load. So as a result, reflection coefficient will be 0. And that is the purpose of using double stub matching circuit. We want to match our load. Okay. So this is now a new configuration. So this is known as series double stub matching circuit. So if you look at the two possible double stub matching circuits, so you can clearly see that there are two design parameters that as a microwave engineer you will find out, that is L1 and L2, because this distance is fixed. So we don't need to do any calculation for the distance. Only we need to do is to find out that for a given load, what should be L1 and what should be L2 so that we get this condition. So it means for double stub, what are the design parameters? So this is design parameters L1, which is the length of stub number 1, and L2, which is going to be the length of stub number 2. Now you all know that from single stub matching circuit, if you remember, the length of the stub depends upon how much reactance or how much susceptance we require from our stub. Because let me again refresh your memories. What is stub? Stub is either a short circuited transmission line or open circuited transmission line. And we have uh, found that a transmission line which is short circuited or open circuited, its behavior is such that its impedance Zin. So if it is open circuit, this input impedance is equal to minus j z naught cotangent beta L. And it means that this is some kind of a number and it depends on the length of the stub. So from a stub point of view, this is L1. So if L changes, this number will change. And because this L is an argument of cotangent function, so if you put different values of L, so cotangent theta will change. And we know that cotangent is a trigonometric function whose value can vary from minus infinity to plus infinity. So it means that we will get some number which can be minus as well as plus, and it can be x because this is imaginary number. So it means it depending upon how much is the length, we can find out the corresponding reactance. Similarly, if the stub is short circuit, this is L, this is Z. So how much will be Z in? It will be simply J Z naught tangent beta. Again, this is purely imaginary. So again, cotangent can be negative as well as positive. So again, you will get minus plus Jx. So it's obvious that how much is X, it depends on the value of L. Okay. So again, how much we need reactance. So when we connect stub at this position, so we will find out how much is the required susceptance. So let's say we may require minus plus jx. So once I know how much x1 I require, I can find out the corresponding length. Similarly, the purpose of connecting step number 2 is it can provide us minus plus jx2. So once I know how much x2 is my requirement, so once I know x2, I will find out m. Okay. So it means once we know x1 and x2, then we will be able to find L1 and L2. Similarly, it's also important that you remember this thing that when we are dealing with series circuits, we operate in the impedance or reactance mode. And when we deal with the shunt configuration, we deal with admittance. So in this case, because stubs are connected in parallel configuration or shunt configuration, So in this case, you need to remember that if the impedance is given, if load is given to you in terms of impedance, so the first thing you need to do is convert this impedance into corresponding admittance. So ZL will be represented in terms of YL. Once you do that, then this stub is connected in shunt. So the effect of this stub will be, it will provide us some susceptance. So I will represent this by, let's say, B1. So once I know how much B1 I need, I will be able to find out L1. Similarly, the stub 2 will provide us minus plus JB2. So once we know how much B2 is required, then we will be able to find out L2. So in both these circuits, our goal will be, first we need to find out what should be B1. Once we know that, we will be able to find out L1. Similarly, in this next second step, we will be finding out how much is B2. Once we know B2, then we will be able to find out L2. And for series connection, once we know X1, then we will find out L1. Once we know X2, then we will be able to find out L2. So this is going to be our solution process. We will start with finding out how much is the reactance or susceptance that we expect from step number 1. Then we will be able to find out its length. Then we will go to step number 2, and we will find out how much is our requirement of X2, and then we will be able to find out L2. Now we will find out these unknowns using Smith chart. Again, analytical method is also available that you can look into into the textbook that we are using for this course. But from examination point of view, I don't want to check mm, your ability to solve mathematical equations because uh, you need to solve the quadratic equation. So this process will not help you to understand the conceptual meaning of double stub. So when you use Smith chart, then you will understand what this stub number 1 is doing and what this stub number 2 is doing. Because ultimately, if you remember, I have mentioned this point many times in my last lecture that from Smith chart point of view, how I will know that my circuit is mismatched or how my circuit is matched. So on Smith chart, if impedance is not at the center, it means your circuit is not matched. And with the help of these two stubs, once we connect these two stubs, what will happen that the impedance which was not at the center initially, it will come to the center of the Smith chart. So after completing the solution, you will find out that now you will be exactly at the center of Smith chart. So no matter whether you use L network, whether you use single stub, whether you use double stub, whether you use quarter wave transformer, ultimately you will find out that once you use impedance matching circuit, you should be at the center of Smith chart. So we will find out that once we take into account the effect of stub number 1 and stub number 2, we should be at the center. Okay, so let's do one example so that you understand this whole process. So it doesn't matter whether you are solving shunt double stub matching circuit or whether you are solving series double stub matching circuit, the solution process or the solution steps are same. Okay, the only thing that you need to make sure is when you are solving shunt circuit, you should make sure that you are operating in the admittance mode. And when you are solving a series circuit, you need to make sure that you are operating in the impedance mode. So with that background, let me solve one example. So the example that we are going to solve step by step is for this situation that there is a load which is equal to 60 minus j80 ohm. It is connected with a transmission line 50 ohm. So even from this information, you can clearly see that ZL is equal to net Z naught. So it means we have an impedance mismatching problem. Now we are asked to design a double stub circuit for that. So design a double stub matching circuit using open circuited stub. So our limitation is that we have to use open circuited stub. But you know, we once, even if I change this problem, even if I ask you to design a double stub, but using short circuited stub, you can also do that. And we will discuss that point as well. Using open circuited stubs that are spaced lambda by 8 apart. Frequency is also given to us. We need to design this circuit for 2 gigahertz. So this is the information that is given to us. Let's also confirm, yes, double stub matching circuit using open circuited stub that are lambda by 8 distance apart and are connected in shunt configuration. So now these are important points that you need to take into account in your solution. One is that distance is given to you. This is D. As I was talking about, the commonly used distance is either lambda by 8 or 3 lambda by 8. So in this problem, we are using lambda by 8. The other important point is we are asked to design a circuit using open circuited stubs. So that is also important point. And then finally, we are also designing a shunt configuration. So it means our circuit will be like this. So it's always better to draw the circuit when you are solving a problem like this so that you don't make any mistake. So it means now this is the problem. We also are going to use open circuited stub. So let me remove this. Now, if you remember, I mentioned this point that whenever you are designing a shunt circuit, if load is represented in terms of impedance, the first thing you need to do is transform load impedance into load admittance. Load admittance. So this is also important point to consider. So that is why I have encircled this as an indication that we are given load in terms of its impedance. So we should do the first thing that we need to do on Smith chart is to convert load impedance into load admittance. Okay. So with this the little bit background, so how we are going to solve this using Smith chart. So as always, whenever you are using Smith chart, the first thing that you need to do is normalize the load impedance. So 1.2 minus J 1.6. And then find the location of this point on Smith chart. Locate it on Smith chart. And once we locate it on the Smith chart, then the next thing we will do is to transform this ZL dash into YL dash. And you people, I think you will now never forget that on Smith chart, how to transform impedance to admittance or admittance to impedance is to draw a line from the position of the ZL dash connected to the center and then extend it on the opposite side with equal distance. Okay, so the same mechanism that we will use. So now let me show the Smith chart. Okay, so the point that we are interested is again, this is 1.2. So this is the resistive circle, and where is the so this is 1.6 that you can clearly see. So this is 1.6 reactive circle, and this is 1.2. So the point at which they will be intersecting, we just need to mark that. This one. So this is our ZL dash 1.2 minus J 1.6. So you can clearly see where I have located this. I have located it at minus 1.6 circle and 1.2 resistive circle. You can clearly see that they are intersecting at this point. This one and this one. Okay. So this is how you will locate. And then what is the other important point in case of double stub? The distance between the two stubs that is given to us is equal to lambda by 8. So in double stub, there will always be some distance between the two stubs. That will always be fixed. It will be either lambda by 8 or 3 lambda by 8. Whenever distance is given equal to lambda by 8, then what you need to do is you need to draw. So let me write this statement. Draw 90-degree rotated 1 plus dx. I've used this terminology many times, so I think now you people will already know whenever I use this term 1 plus jx circle, so you should know which circle I'm talking about. Okay. So this is the case in this example that distance is lambda by 8. So when distance is like this, what you need to do, you will draw a 90-degree rotated circle, and I will talk about how to draw that. But in some problems, it will also be given that distance between the two stubs is 3 lambda by 8. So what will change in this type of problems? When distance is like this, then what you will do, you will draw 270-degree rotated 1 plus x circle. So let me draw, because we in our example distance is lambda by 8, so I will draw a 90-degree rotated circle. And once you know where I am drawing it, then you will be understand if such type of problems are given to you, then where will be this 270 degree. Now, okay, so with this background, let me uh, go back to the. So how we will draw the 90-degree rotated circle? If you draw a line, vertical line, right at the center of Smith chart. Okay. So this is the line that you need to draw on the Smith chart that you will have, and then find out the center of this line. So up to this distance. So this line, if it is of 8 centimeter, then the center will be at 4 centimeters. So you need to, with the help of a scale, you will have a scale with you. So you will find out that, let's say this is the center of this line. Okay. And then where is the 1 plus jx circle? So let me mark that. I have used it many times. So actually, this is the circle that I am referring to as 1 plus jx circle. This one. So this is over 1 plus jx circle, which is already there on the Smith chart. You need to don't need to draw it. Okay. So let me also mark it so that you remember that I'm talking about this circle, the circle which is passing through the center of the Smith chart. And that is why it's 1 plus 6. So actually I'm talking about this circle. So what we need to do is we need to rotate this circle by 90 degrees. So right now it is at this point. So 90-degree rotation means that this will come to this point. Okay. So with the help of a compass, you need to draw a rotated version of this circle. So again, I am drawing a rough version, but you need to practice this with the help of compass. This will be the center. And then how much you will open it? You will open your compass with this much radius up to this point, and then you will draw a circle. Again, let me draw it, not exactly, but you should get an idea that this is how your circle will look like. Okay, so what I have drawn, draw rotated 90-degree 1 plus 6. So this is the main point that I will continue with the next session, because this session is about to finish. So the main point that you have learned from this session is that whenever a double stub impedance matching circuit is designed using Smith chart, you have to draw this circle. How much it will be rotated? It will be rotated by 90 degree if distance is lambda by 8. And now you know, if the distance is 3 lambda by 8, then it will be rotated by 270 degree. So this is 90, this is 180 degree. So this is 270. So in this case, your circle, rotated circle, will be somewhere at the bottom of the Smith chart, somewhere over here. Okay.